Hi, I'm Michael Kaneski. I'm PhD in the Department of Computer Science of the Federal University of Minas Gerais. Today I present a work that I did in collaboration with Ricardo Ferreira, José Nassif, and Fernando Pereira. The title of this work is Polynomial Time Exact Solution to the Bit-Aware Register Bind Problem. We shall present an optimal solution to the problem of minimizing the register bank produced during the high-level synthesis. HLS, as we call it, is the problem of mapping an given program written in some programming language onto some hardware, which we can synthesize, for instance, on an FPGA. This problem that we care about in the paper concerns the minimizations of the number of bits necessary to allocate resource. Bit-width minimization has been historically solved by algorithms that perform register assignment and compilers. This problem consists in finding the minimum number of registers necessary to compile a program. Register assignment is NP-complete in general, as the subsums graph coloring. However, since 2005, it is known that register assignment has a polynomial time solutions when restricted to program in static single assignment form. Because SSA form, programs have chordal interference graphs. Those results related to register assignment is SSA form programs concerning traditional compilations in which registers have all the same length, usually power of 2, for example 8, 16, 32, and 64. However, in hardware synthesis, nothing hinds the synthesizer from using resources of different bit widths. So, in this setting, register assignment is NP-complete, even for SSA form program, and even if only two sizes of registers are admissible. In this paper, we revisited the register bind problem, a variation of register assignment in which neither the number of registers nor their bit widths are fixed. We show that optimal register bind admits polynomial time solutions and Pereira and Paulbersberg elementary program representation. And then we developed a new register bind algorithm as a proof of concept. The algorithm is formally described in the paper. Also, we compare our optimal algorithm with two approximate solutions to register bind, the Cognizant and Brisk's method. To explain what we did, let's consider this problem here. We wanted to allocate the variables in this program into register. The variables have a different size. The size of a variable is the number of bits that we need to represent that variable base 2. For instance, variable A has 5 bits, and the variable don't have all the same size. Here you can see the size of the different variables in our example. There are different ways to pack those variables in register. One of the early techniques is due to Philip Brisk. We shall call it Brisk's method. This method consists of using the coloring of interval graphs to assign colors to the variables in the straight line program. A list of free and taken register is updated at each program point in ascending order. Whenever the last use of variable is visited, its register is returned to the free list. Whenever variable is allocated to a register, this register is inserted into the taken list. Then we have taken in the first register the variable A. Next program point, we have taken the variable B into a second register. Next, we have taken the variable C into the third register. When we get the variable D, the register with 6 bits and is list free because the variable B is dead. This way, the variable D will be allocated to the second register. This case is interesting. We only have a register with 4 bits in the free list. So to solve this problem, we resized the register to 7 bits and allocated to variable E. And finally, we finish with the list taken empty and the list free with the register used. A second solution to the same problem is due to Jason Kong from UCLA. Kong et al. Have proposed a heuristic to solve the local register bind problem, which generalizes previous documented technique. Contrary to Brisk et al.'s method, this algorithm has designed to accommodate variables with different bit widths. Kong's et al. Algorithm is also grid. However, instead of interacting over the introductions in the program, it interacts over the widths of the variables defined by those instructions in descending order. The algorithm packs into the same register variable of similar bit width. Thus, we start with register in order and insert the variable into the register, in this case variable A, use only 5 bits. Then we insert into a register with this size. Next, we insert variable B in a register with 7 bits. Of course, the variable B could be inserted into the register with 6 bits, but due to variable E, which will appear in the future, we can reuse a larger register. And continues to fill the register each program point, we insert variable C in register with 4 bits. In the similar way, we insert variable D in register with 3 bits. And finally, we finish the program point by inserting variable E in the register with 7 bits. If we compare to Brisk and Kong's method for the example, we see the Brisk has less register quantity in the total bit size was less too. However, if we consider another example, change the order in which the variable appears during code execution, we can see the Kong solution was better than Brisk's solutions. So because of that, this motivates us to looking for a new algorithm bind register, which we could get the optimal register number for all benchmarks. Let's go back to the first example. We are going to introduce the new algorithm which will use swaps insert on the register assignment. Local register bind becomes straightforward when performed in the elementary format. In this representation, local register bind is equivalent to solving multiple instances of the weighted graph column problem on elementary graphs. The union of two Krig's forms elementary graphs. The figure on the screen shows the program converted into elementary form. First, we split each part of life range. Next, we parallel copy each split life range of the variable. Next, we shows a solution to union the register. Each register receives a color and the minimum color is the number needed register in the assignment variable. Continues to the program point, we get an interesting fact. Looking to the red box, we can minimize of the list of registers using to compute the minimum sum of difference between two lists of equal length, key1 and key2. Sort them in ascending order and pair up elements with the same index. This part is important because we will insert a swap into this change. And we finish the algorithm. Therefore, we can find the best solution insert swaps on the register assignment. For the first example, the hardware synthesized with 3 registers, which added up to 16 bits. A swap between register R1 and R2 is necessary to exchange variables C and D, like it shows in the figure. And that concludes our example. In the paper, we provide answers to 3 research questions. The first one is about the compilation time, which we were looking to measure the time taken to do register bind. The second one is about register minimization, which we were looking to measure how does the optimal algorithm perform in terms of number and size of register. And the last research question is about the number of swaps which we insert during the bind of the register, which we were looking to verify the number of swaps must be set to ensure optimal binding. So let's focus on the second research question about register minimization. I will show on the x-axis a number of functions taken from my bench. Functions are sorted by their size in bytes. The y-axis shows the size of the register banks in bits. Remember, each tick in the x-axis represents a different function. The lower a curve, the better for the method. Thus, the swap-based approach in Brew is yielding the best results. This result was expected as a consequence of that approach's optimality. The difference to the other allocators is small, which Kong's method showing a slight advantage over the other techniques. Let's group the functions per benchmark from where they come. In this case, benchmarks are organized in this x-axis. And the y-axis shows the bandwidth relative to swap method. In our case, our algorithm was better than the others. Consider the size of the register bank that it generated. The Kong's methods on average was second place, and the Brisk methods took third and fourth place. This paper has introduced an optimal solution to the bit-aware register bind problem. This algorithm finds in polynomial time the smallest register bank for any sequence of instructions. Compared to the previous solutions to that problem, the new algorithm remains optimal in the presence of branches. In spite of these positive results, we do not expect this new algorithm to make prior heuristic obsolete. Our solution to register assignment, although polynomial time, is still slower than preceding state-of-the-art techniques to solve the same problem. In this regard, our experiments have shown that techniques such as Kong's or Brick's methods still leave room for improvement, as they fall behind an optimal solution by 6 to 20%. Thank you for watching, and any question let me know.